This is my Lab 3 presentation. So in the first part, we're going to analyze the motion of a star around a black hole to determine mass of black hole, and we got that it was 2.4 times 10 to the 34th kilograms. In part 2, we're going to determine the initial velocity of a spaceship in order to get close enough to the black hole without crashing, and allow it to still leave the system. The vector is going to be 2.67 times 10 to the 4th for x and y, and then 0 for z. It's going to demonstrate Newton's second law and its relationship with momentum. So for part 1, the system is a star and the surroundings are the black hole in space. The equations we're going to use for this entire lab are going to be that force is equal to change in momentum over change in time, parallel and perpendicular components added up equal net force, and we have the velocity update formula. We also have the force of gravity, which we'll use to, as many of the objects in the sun exert a force of gravity on other objects. So for the first part, we have our gravitational constant, the mass of the star, total time, yada yada. So in order to find the mass of the star, we're going to start by computing our initial and final momentum vectors, and then we're going to use that to get delta V and delta P, and from there we can calculate dP over dt, which is our net force, and then we can calculate from that parallel force, and then we can subtract from our total force our parallel force in order to get our perpendicular force. And using this information, we can find the radius of the star by dividing by the perpendicular magnitude, which would be distance. And then from there, we're going to use the gravity equation to get the mass of our black hole. And then this is all just updating the visual, which is this. Okay, so for part 2, surroundings of the spaceship, our system is a spaceship, surroundings of the planet and the moon, initial conditions all given up here. We assume it takes a month, and of the moon, and what we determined. Okay, so for this, we're going to start by calculating the radius from planet to moon, and then using this and the unit vector of the radius, we're going to calculate the force of the planet on the moon. Using a similar thing, we're going to find the ship on the moon, and we're going to add those two to get the net force of the two objects on the moon. Then we're going to go about that same process in order to find the magnitude of the planet on the ship. And so now that we know these, we can determine how the moon is going to move by doing our velocity update and our position update. And then we can also use the magnitude of the force on the ship in order to determine how the ship is going to update with velocity and position. So that is going to kind of show us if our initial velocity is correct or not. And then we have down here, which is our error redundancy things. So this is kind of what we get with the initial velocity of 2.67 times 10 to the 34th, comma 2.67 times 10 to the 34th. That should be a 4, and then 0. Okay, so now we have some questions. How is net force different than change in momentum? Mathematically, these two are the same, but you can infer net force by changing momentum instead of adding up every single force. For both of these, parallel is just going to be tangential acceleration or velocity. Perpendicular is just going to cause the change in direction. Net force is going to be responsible for the change. Net force causes a change in motion, and momentum is the reflection of that change. So for part 2, it asks, what would be different if we had a black hole in the system? And the answer is the model would need to account for the force of gravity of all the objects, and large/closer objects have more gravitational force, so black hole will dominate the interactions of these other two. So possible errors, this is all approximation, so it may not accurately reflect reality, and it also assumes there are no outside forces acting on the spaceship. And then also trial and error, since part 2 was obtained through trial and error, it might not be the best fit, but it is a good fit. So overall, that is what we've learned today. Thank you for watching.